All right, so carrying on to section 5.5, substitution, integration by substitution. This is going to be one of those sections where we kind of dial back the theory and just do a bunch of examples. So I know folks tend to like that sometimes, so I hope you enjoy this. So, okay, so here's what we're going to get. This example, the integral is 5x times the square root of 1 minus x squared. All right, in the first example I said we could just multiply this out and turn it into a polynomial. That's not the case here. All right, so in this instance, we really don't have any, we really cannot apply the simpler strategies that we learned back in 5.1. So in this case, our only recourse is u substitution. So let's see where our composition of functions is. Our composition of functions is right here, right? It's this square root of 1 minus x squared. So let's do a u substitution. U equals 1 minus x squared. Okay, then, by the way, our du is going to have to be the derivative of this with respect to x, which is negative 2x, and then times dx. Do we have negative 2x? No, we have x, right? We have x multiplied on the outside along with 5, but we don't have the negative 2. No worries, no worries. We might not have exactly what we want, but we have at least a constant multiple. So what we're going to do is let's divide both sides by negative 2 here. So we have negative 1/2 du equals x dx. So now if I go back and I find my, my x and my dx, those two together are going to be replaced by negative 1/2 du. And with the negative 1/2, since it's a constant multiple, I can actually put it in front of the entire integral, negative 1/2, and then I'm going to put the du at the end. Now, with the variable substitution here, I'm going to get to replace the 1 minus x squared with u. But I'm still going to have this 5. So I'm still going to have a 5, and I'm still going to have a square root, and then I'm going to have a u underneath here. So that's what I've got now. Now the 5 can come out of the integral as well, so this is negative 5/2. And now we're integrating the square root of u. Now, we can do that because that's just a power function, right? That's u to the 1/2. So what we're going to get here is u to the power 3/2. Then we'll have to divide by 3/2 by the anti-power rule. So this would be times 2/3. That's the same as dividing by 3/2. And then, of course, we'll have a plus c on the end. So what we end up with in this problem, we have negative 5/2 times the 2/3 we got from the anti-power rule. So the 2's can cancel, and we get negative 5/3. And then we have u to the 3/2, but let's replace the u with 1 minus x squared, and then that to the power 3/2, and then, of course, with a plus c on the end. So that's our antiderivative, and you can check it again. You can check that, take the derivative of this, and you should get 5x times the square root of 1 minus x squared. Done. So, all right, there's our first example. So, second example. Sorry, I called that example 2 because we did an example on the in a previous video. So, let's do example 3. For this one, I'm going to do sine of x times cosine of x dx. Okay, sine of x times cosine of x. Well, that's interesting. Sine and cosine are not exactly, but pretty much, like, in one way or another, they're kind of like derivatives of each other, right? Like cosine is the derivative of sine, and sine is not the derivative of cosine, but it's the opposite of the derivative of cosine, right? So in a way, here we almost have two different options for how we approach this. One option is to let u equal sine of x. Then du will be the derivative of sine of x, which is cosine x, times dx. So for the differential substitution, we'll use cosine x times dx. That'll give us du. And then the entire rest of the integrand, right, the sine x here is going to be our u. So when we do our conversion, we'll get the integral of u times du. And that, we get just 1/2 u squared, right? Just use the anti-power rule on that with a plus c. And then we undo our substitution and get 1/2 times sine squared x plus c. And that is our antiderivatives. That is the solution to this indefinite integral. But this is only one of two different approaches we could have taken. So, or the other option would be to say u equals cosine of x. And if u equals cosine x, then what we've got is du is going to be negative sine of x times dx, and the negative's not there, right? We've got the sine, but we don't have the negative. So we can move the negative over, and then we can say, okay, so now this is going to equal, so bringing this down here, this is going to alternatively equal the negative integral of now sine x dx is my du, and then the cosine x is my u, so I've got u du again. I've got the same thing, right? The only difference is this time with our differential substitution, we ended up having to stick a negative in there. That's all. So we get negative 1/2 u squared plus c, and this time I have negative 1/2 cosine squared x plus c. And that is also a correct antiderivative. So both are correct. Okay? Both of these are correct. Two different methods give us two different answers. And you might think to yourself, those are different functions. 1/2 sine squared x is not the same as negative 1/2 cosine squared x. However, there's a plus c on the end. Don't forget the plus c. So I'm not going to answer this question for you. I'm just going to leave it. I'm just going to leave you with this question. Why are those actually both correct antiderivatives? If you're curious about that and you want to talk about it, just let me know, and I'd be happy to discuss it.